Okay, our next paper is entitled Multistatic Pulse Wave Angle Variable Assisted Relative Interferometric Radar. It's going to be given by Jonathan Friedman.
Okay, before we get started, a few quick things. I first apologize for the number of adjectives in the title. It should hopefully seem necessary after the talk. Secondly, not to scare anyone, there are approximately 25 slides. I will skip a few, but I have rehearsed this talk. My average run time is 17 minutes and 23 seconds, which should fit very nicely in our 20-minute time slot with some room for questions. I am unfortunately recording this. I'm just a PhD student. My advisor wanted to see my talk. He couldn't be here today, unfortunately, so I'm stuck with the camera. Consequently, I would ask that you hold all the really hard questions that I will have a hard time answering until, like after I shut the camera off. And lastly, I would like to say thank you for letting me come here and speak to you guys today. I am sufficiently starstruck by the quality of the engineering researchers and scientists and practitioners in the room today. Believe me, I present this with a requisite amount of humility. So, with that said, let's get started. So this is Multistatic Pulse Wave Angle Variable Assisted Relative Interferometric Radar. I'm Jonathan Friedman. I'm from the Network and Embedded Systems Laboratory at the University of California in Los Angeles, more affectionately known as UCLA. Now, to get started on this multistatic, I think we'd offer you a brief reconception of the definition. Traditionally, we think of multistatic, we're referring to one transmitter and a plurality of receivers. For the purposes of this talk, I'm going to redefine that as a duality of transmitters, so two or more transmitters communicating with one or more receivers. In a sense, it's very similar to like the GPS type architecture where you have a fixed set of transmitting infrastructure and a near infinite set of receivers. And to kind of set the problem up, we're going to start with the monostatic common radar. And basically, we're determining position of targets based on an angle, which comes from using a very narrow beam and electronically or mechanically positioning that beam, and then a range or a distance, which comes from the echo time of flight. And the problem fundamentally with this approach is that angle-based schemes degrade. They degrade linearly, which is nice, but they ultimately degrade. So that when we get large position errors at large range from small angular errors. And ultimately, our problem with fixing this is that we have to reduce the amount of the beam width that we have, which has the effect of one, being difficult to do, and second, increasing the scan time because we now have more angles to move through. Okay, so to kind of illustrate this, not to you guys who are well aware of these concepts, but to my colleagues, we set up this test bed. We were using a commercial NARDA reference horn, and we mounted on top of a precision pan tilt unit. That's basically just a simplified motion control platform. And then we used these small 2.4 gigahertz ISM band transmitters. They're basically have to be non-FCC compliant, and they transmit continuous wave at relatively high powers. We then position them onto this very scientific piece of poster board and scan the unit around, and this is what we see. Now the interesting thing is you can see a lot. I mean, this is a very simple setup, but you actually can see a lot. You get a lot of information from this. If I had to, destroy these targets, a sufficient amount of explosives, and I'm done. The problem though is that we really want to see better. We want a clearer picture, and if we want to do better, we need more data. And we don't want that data to come from tightening the beam width because it's difficult to do and it will hurt our scan time, and it will cause greater transmitter exposure by more repeated transmissions in the small angles. So this led us in 2008 to a work we presented at Milcom called RE, Angle Variable Assisted Relative Interferometry. At the time, we didn't realize that was the continuous wave version because it wasn't until later that we realized, hey, wait a minute, if we pulse this thing, we get a few interesting benefits. And that's the RADARCON work, which I'll get to after this introduction. Now, again, as I mentioned in my introduction, I'm well aware this is beneath you guys, but to give you the quick overview, when you transmit with two transmitters on the same frequency, the superposed signal that's detected at the receiver is also at that frequency. And you basically, for all practical intents and purposes, can't disambiguate them. However, if we transmit at different frequencies, the superposed signal has this beat envelope. And a beat envelope is a frequency that's at the frequency difference between the two transmitted frequencies. So this is what led us to angle variable assisted relative interferometry. So what we have here are two transmitters. The transmitters transmit pairs of frequencies. Those pairs are each at a unique frequency, as you can see here and here, but the difference between them is shared. So this spacing and this spacing is the same. As a result, we have envelopes that are common frequencies, and we can do phase differencing at that common frequency, where phase differencing is meaningful. And at the same time, we preserve the identity. So this is what that looks like. Now, because we preserve identity, we're able to disambiguate all the way across the 180-degree phase spectrum, which is we can say that transmitter A is phase leading transmitter B because we know these identities. We can make that distinct from transmitter B phase leading A. And this is the hyperbolic phase lines you use. Sorry? Seems a little touchy. Okay, so these are the hyperbolic phase lines you get from this phase difference. And the reason we use the phase difference instead of the absolute phase is that if we were to use absolute phase, we get extremely tight time synchronization between the transmitters and receivers. That's somewhat impractical to do because it requires the receivers to transmit back or to maintain some sense of sync, which might expose the location of the receivers, but also because it will ultimately degrade to just a time of flight system, which is more complicated.